Hello everyone. We are going to discuss section 10.3, phase transitions. This is a section that we'll spend a few videos on. Phase transitions are one of the more important ideas from this chapter that we want to discuss. So for this particular video, the learning objectives are define phase transitions and phase transition temperatures, and also explain the relation between phase transition temperatures and intermolecular attractive forces. The last learning objective will be covered in a separate video. So let's get started with this. Some of this is very straightforward and things you may have learned in, around third or fourth grade. But there's actually a bit more going on that we want to clarify with some of these phase transitions. So we'll start by looking at vaporization and condensation, and this is actually the most complex of these. These are opposite processes. As we look through these, they will always have these opposite processes where one is describing the phase transition in one direction and the other is describing it in the other direction. So when we have a phase transition from the gas phase to the liquid phase, we call that condensation. So anytime you see a liquid forming, and you might see this, on the outside of I guess on the commercials for certain beverages, they'll show, zoomed up pictures of these little water droplets forming on the outside of a cool beverage. So that's a condensation because the gas in the air has condensed. Although if you're just pulling it out of some water, that's not condensation. But if it's a gas forming from outside turning into a liquid, we call that condensation. The reverse process is called vaporization. So this is when a liquid turns into a gas. Now there's one thing we have to consider with this particular set of transitions, and it's actually true for all of them, but this is the one where it comes up the most in terms of how it's applied. And that is the idea that we have something called a dynamic equilibrium going on here with these phase changes. And equilibrium is something that will be explored in more detail in the next semester. But the idea here is that we have this transition from one phase to the other at the same time. That's going in the reverse direction. So we have condensation happening at the same time as vaporization is occurring. And if we allow this to reach what we call equilibrium, we'll have a certain amount in one phase versus the other. For specifically gas phase, we can measure this as the vapor pressure. So at equilibrium, there will be a vapor pressure of a liquid. So you have a liquid, and then you have a certain amount of that liquid that goes into the gas phase, and we call that the amount of that the vapor pressure. Now it turns out that this property is dependent upon the temperature, as we'll see, as well as intermolecular forces. So let's talk about this a little bit more from the perspective of what is that liquid doing. So we have a graph here showing the kinetic energy of a particular molecule in the liquid phase, and then the number of molecules that have that particular kinetic energy. So when we have a low temperature, we have this sort of a distribution. It's a tighter distribution. By tighter, I mean the distance from one side to the other of this sort of bell curve is smaller, and the peak is a bit higher. At a higher temperature, we'll have a different distribution where there's a few differences. One is that you have a wider, the wider from one side to the other. The peak is lower, and it is at a higher kinetic energy. So as we increase the temperature, what we'll see this trend of, bell curves that kind of get higher average kinetic energy and greater overall width of the curve. And then we have this point right here. This point is the minimum kinetic energy needed to escape. And what that means is that it's escaping the liquid phase and becoming a gas. So what happens here is that when you get when you get above this point, you're going to have the liquid enter the gas phase. And what the difference between low temperature and high temperature here is that at a higher temperature, a greater number of those molecules can escape the liquid to go into the gas phase. So the reason I'm bringing this up is because this is a unique thing to the transition between liquid and vapor, in that as you as you increase the temperature, you're always having some in the vapor phase, but you get more and more as you increase it. And I want to, let's see, do we want to get into, okay, what we're going to do is we're going to look at boiling. We'll talk more about how this distinction relates to some things that go on with the boiling points. Okay, so a boiling point, at the boiling point, you have, again, transitions from liquid to gas. What is different, though, is that this is a particular temperature at which the vapor pressure, so we've already talked about vapor pressure up here as being, there's an equilibrium amount that is present. At the boiling point, the vapor pressure is equal to the atmospheric pressure around it. So whatever surroundings that liquid is in, the vapor pressure is the same as the atmospheric pressure. And what that will essentially do, if we look at this set of curves up here, it's as if this bell curve has the highest point right on this minimum kinetic energy needed to escape. So suddenly, all of the molecules, or most of the molecules, have exactly the energy that they need to escape. So what ends up happening at the boiling point is all of the gas molecules are trying to escape at the same time. And you end up forming these large bubbles of gas that escape from the liquid. The normal boiling point is when that pressure happens to be exactly 1 atmosphere. So here we're showing a graph of some different liquids and their vapor pressure as a function of temperature. So as the temperature changes, what is the vapor pressure? When we are at this dotted line right here is atmospheric pressure. So when we are at that pressure, we can see what the boiling points will be for these. So liquid, of course, or water, of course, we know has a boiling point of 100 degrees Celsius. Then we can see these other liquids where they are, and this one, is not really close to its boiling point yet. But we can also see how there are these curves here that describe the vapor pressure as we approach the boiling point, and they all tend to have a similar kind of shape to them. That shape is described by this equation called the Clausius-Clapeyron equation. I think there might be a homework question on this, but this is not something I want to spend a lot of time on. It will not be on the exam, will not be on the quiz, but there is an equation of a similar form that comes up in Chemistry 1B, and it's an equation we'll focus on quite a bit. So it is not a waste of time to look at this if you are going to take Chemistry 1B. So, go ahead and do that homework question if that's your goal. But it's not something we're going to spend a lot of time to focus on in this course. So I wanted to say what that was. It's the equation that describes what's going on up here. And you can spend some time on that if you would like to, but will not be on the exam. So there's some examples here of using that. And when this phase change occurs, whether it is a single molecule or you have all of those gas bubbles forming at the boiling point, we have this energy associated with that phase change. So it's called the enthalpy of vaporization. So it's the energy to go from liquid to gas for that molecule. And we're showing what that is here for water. And it turns out that that energy is exactly the same for condensation as it is for vaporization. The exception being, of course, the sign, right? So vaporization is endothermic. We have to put energy in to cause that phase change to occur, whereas condensation is exothermic. Energy comes out of that while that phase change occurs. An example of an exothermic condensation is if you get a steam burn, because the steam is condensing on your hand, if the burn is on your hand, and as it's doing so, it's putting all of that energy into your hand, which is what causes the burn. So you want to be able to do calculations with this, and we'll talk more about those calculations in the next video. I did want to mention one thing related to this, however. So when we think of things involving water vapor, we often think of or being in water is a good way to say this. When we think of water, we think of cooling down, right? And the reason that happens, and there's a little discussion about that here, when you have water on your body, that water is, some of it is evaporating because of the vapor pressure. You're going to have some that will evaporate, and when that happens, it is using up this amount of energy. So that energy is probably coming from your body. So that evaporation will cool you down. So when you get out of some water, you sometimes feel cold. That is the reason for that. However, that effect is smaller if you're in a humid region because there is already a higher vapor pressure. So there's not as much of that water leaving your skin going into the gas phase. Okay, so just a little bit of a qualitative discussion about that, and we'll do some of the calculations a bit later. For now, we want to focus on understanding all of these phase transitions. The next two are melting and freezing. Again, we're doing these in pairs. So melting is a solid becoming a liquid. Freezing is a liquid becoming a solid. Of course, you probably already know that, right? So that's one of those ones you've known about for a while. And the energy associated with this change is called the heat of fusion. And so the heat of fusion is the energy that is necessary to cause a solid to become a liquid. It is the same energy that is released when a liquid becomes a solid. And that this one would be exothermic, so the sign would be reversed. The temperature at which these occur are the melting point or the freezing point. It is the same temperature either way for that particular phase change. The last one of these is called, the last pair are sublimation and deposition. So there are some solids that under certain conditions can go directly from the solid phase to the gas phase. This process is called sublimation. An example of this would be dry ice. Dry ice is solid carbon dioxide, and it goes directly from solid to gas without becoming a liquid first. The opposite of sublimation is deposition. In deposition, you have a gas that turns directly into a solid without first becoming a liquid. So examples of this would be if you have some freezer burn in your freezer, that is a deposition where you have ice that goes from ice to water vapor, and then from water vapor back to ice at a different location within the freezer. Okay, so that is the third of these pair of phase transitions. And an example here of sublimation here for iodine. We have solid becoming a gas, and this gas is a gas that does have a color to it. So you can see that purplish color. Like the others, we have an energy, so heat of sublimation, going from solid to gas, and then the reverse of that is the heat of deposition. They would both have the same energy. And then it turns out that you could have some combination here where you have, if a solid goes directly to a gas, the energy there would be the same as the combination of these two. So solid becoming a liquid, so melting, and then vaporizing. So heat of fusion, heat of vaporization. If you add those together, you'll get the heat of sublimation, because you're ending up going from solid to gas here, whereas here you go solid to liquid, then liquid to gas. So you can add those up in that way. This is basically going back to the thermochemistry we did earlier, where you can look at going from initial to final and add things together like that. And here we're showing graphically how we would do that. So heat of fusion plus heat of vaporization equals heat of sublimation. Okay, so I think we'll leave off there. In the next couple of videos, we'll be looking at some applications of these ideas in terms of looking at what are called heating and cooling curves, as well as looking at phase diagrams.